Hello everyone. In this section, we are going to solve some special differential equation. It's called the separable differential equation. So firstly, I'm going to give you the definition and let you know what the separable differential equation look like. So definition 1, let's take a look. Firstly, it is a first order differential equation. Okay. First order differential equation is called separable. If it can be written in this form. So in the form, we can separate y and x. So let's take a look. It's going to be like this way. Py dy dx equals qx. If we can write our differential equation like this way, then it's called separable differential equation. Or the other way, py y prime equals qx. Another notation, right? So this is called separable differential equation. I'm going to give you some examples of the differential equation. So pretty easy to see. So let's take a look. dy over dx, which is 2xy. Okay, so in this case, you can see we can change this into the definition. If we divide by y, so it's going to be 1 over y dy dx, both sides divided by y, so 2x. So this is like a py dy dx and a qx, right? Qx. And another one, which is dy over dx, which is y squared over x squared plus 1. So same thing, it's going to be 1 over y squared dy dx, which is 1 over x squared plus 1. Actually, why we call that separable differential equation, you can think this way. If we look at here, from definition, if we multiply this equation by dx, so you can see it becomes py dy equals qx dx. So if you look at this equation, on the left side, we only have y. On the right side, there's only x. There's no y. So x and y can be totally separate. So this is called the separable differential equation. Let's see. Next, we are going to solve the differential equation. And before that, we have theorem. The theorem says we can integrate both sides of the equation and find the solution. So let's see. If both py and the qx are continuous, so those py, qx are all in the definition, continuous. Then the differential equation dy dx, which is qx, okay, has general solution. The general solution is px dy, py dy. So it's like we differentiate both sides of the equation, py of this equation. So py dy and the qx dx and plus c, because it's general solution, so we add c, right? Now let's take a look at the real example, and we want to see how to use this theorem or how to solve the separable differential equation. This is pretty easy. First step, we just need to separate x and y. So let's see. Solve this differential equation. First, let's take a look. Is this separable? Left side py, y prime, the right side qx. Yes, it's separable, right? So now let's separate x and y. So that means we only need y on the left side, okay, and we need x on the right side. So here we have dx on the left side, so we multiply by dx. So it's going to be x cosine x dx. So you can see the right side is all but x, left side is all but y. Now we integral both sides. Okay, integral both sides like this way. When we integral, we just do like a calculus 1 regular integration. So integral of 1 dy just becomes y. Is that right? And for the y squared integral, that's y cubed over 3. Okay, the right side. By the theorem, we can add c, but you can add c later. Doesn't matter too much here. We just need a c at the end. And then let's see, for this integral, we need the integral by part. Right, integral by part. And we can skip the calculation. I think it should be okay. So just to change the integral by part is u dv equals uv minus v du. That's the formula, right? So you just set this is u, this is dv, and you solve this integral by part. So this is calculus 2 stuff. And now the right side, I'm just going to find give you the final integral. X sine x minus, okay, the final answer should be this one, x plus c. And this is the solution. Okay, solution. This is implicit solution because we cannot solve for y, right? Let's just give a relationship between x and y. So this is the general solution to the differential equation. Okay, now let's take a look at this one, exercise problem. dy over dx, which is 2xy. So here's the solution. First step, we need to separate x and y. So put all the y to the left side, x to the right side. So it's going to be 1 over y dy, which is 2x times dx, multiply by dx dy by y, right? And integral both sides, okay? And then plus c. Here, natural log y absolute value, and the right side x squared plus c. That's the answer. In the future, we can simplify this answer, but right now, let's just keep this in implicit way. So here's the solution. Now let's take a look at the procedure. When we do, if our differential equation look like this way, fx gy, okay, we know we can separate this, right? We can separate this into 1 over gy, like dy equals fx times dx. But here, we assumed gy is not 0. It's not 0. If gy is 0, we cannot do this way, right? Actually, gy equals 0 will give us a equilibrium solution. I will show you in the next example what's the meaning of this. Okay, don't worry too much. Example 2. Find all solutions to this differential equation. Okay, this is similar to our exercise problem actually. First step, okay, this is given by y prime this way, but because we want to separate dx dy, so we like to write the left side as y prime as dy dx because we want to separate, right? So negative 2y squared x. Let's see. So we say when y is not 0, we can divide by y. Okay, so it's going to be 1 over dy by y squared here, dy, and the right side becomes, when we divide by y squared, the right side left has negative 2x left, and multiple by dx. First step, separate x and y. That's why it's called separable differential equation, because it can be separated. Now, let's integral both sides. Okay. So integral of 1 over y squared should be negative 1 over y. The right side should be negative x squared plus c. Right? And if we simplify this a little bit, this is easy to solve for y. Okay, let's see what the y look like. Both sides multiple by negative 1 and do the reciprocal, so 1 over x squared minus c. Okay. Some students may have question why we don't add c on both sides. You know, because they are all arbitrary constant. When we combine those two, they just become one arbitrary constant. So we don't have to add two constant on both sides, just one. That's okay. And this is the solution, general solution, but this is not all. Okay, because this one want us to find all solution. Here we only did when y is non-zero. So, but for the y equals 0, is a equilibrium solution. Do you still remember what's the equilibrium solution definition? Solution to this differential equation. Yesterday we did definition. For example, yesterday we did in the last class, what's the equilibrium solution? Equilibrium solution means when the y is a constant, make the right side equal 0, right? Is a constant solution. So derivative of this definitely equals 0. So we just make this equal 0. So that means y equals negative 1 and y equals negative 2. So those are the two equilibrium solutions to this differential equation. And if we look at this one, what is constant y can make this equal 0? Definitely y equals 0, right? So y equals 0 is a equilibrium solution. So when we solve the differential equation, please don't lose any solution. We have non-zero solution. Here we also have equilibrium solution. Okay, so we can say just the solution are y equals 1 over x squared minus c and y equals 0. Okay, like this one. I'm going to do another example and then we will do the exercise. Okay, let's try one more. Example 3. dy over dx equals negative 2xy. So the first step, you can say y equals 0 is equilibrium solution. Just in case we forget this solution. It's very easy to forget this solution. Okay, y equals 0 is the solution. We find the one. And the next we separate, because when y is not 0, so when y is not 0, we can divide by y. Negative 1 over, so positive 1 over y dy, separate, right? Negative 2x dx. And this is natural log y absolute value, right side negative x squared plus c. Very similar to our exercise problem, but in this example, we are not going to leave this y in this way. I'm going to simplify this solution. Let you see what's the solution look like. For natural log, this equation has natural log, so we take a e exponential function at both sides, right? So we can, when we have those kind of things, I'm going to write down in the next step. e to the natural log e to the negative x squared plus c. Okay, and please put the position x squared negative x squared plus c in the exponent position. Be careful. And then simplify. Natural log and exponential function, they are inverse function. They just cancel out. Y absolute value equals e to the negative x squared plus c. We are going to further simplify. E to the a plus b, we can change this e into e to the a times e to the b. So this is the law of exponent. It's like x squared times x cubed equals x to the fifth. Why you have the 5? Because we add exponent together, right? So when we have addition in the exponent, we can separate them into product of two exponential functions. So right now, e to the negative x squared times e to the c. Are you okay or what? Next, we simplify. We open the absolute value. So when we take out the absolute value, we do plus minus. Is that right? E to the c. Excuse me. Next, simplify. E to the c is a arbitrary constant. E to the c is arbitrary constant, and the plus minus combined with any arbitrary constant is also going to be a constant. So let's just write down y equals, change everything into just c1. Or you can just use c, doesn't matter. Okay. So this is our final solution. Okay, simplified final solution. Let's try this problem. Solve this. Find all solution and simplify. Why? Okay, find the simplified solution, general solution. Please do this by yourself. I'm going to give the solution. So So the final general solution should be just c1 e to the x squared over 2 and y equals 0. Equilibrium solution. That's all solutions, right? So next we are going to have another example. This is a real life problem. It's called cooling law. Okay, cooling law, like application to the real life. How to solve separable differential equation, and this equation, we get the equation from the real life. So let's see. Example 4. Let's see, here is the example 4. So this problem, we have a hot metal bar whose original temperature is 350, is placed in a room whose temperature is constant at 70. So that means we put some hot thing into the room temperature, and after 2 minutes, the temperature of the bar is 210. Now using Newton's law of cooling to find, first question, the temperature of the bar after 4 minutes. Second, the time required for the bar to cool to 100 degrees. So this is kind of like a temperature problem. Another kind of thing, like if we have hot water, we put in the room temperature. After some time, definitely it's going to be cooling. The water will cool down, right? And the temperature of the water will be as same as the room temperature. So firstly, I'm going to give you the Newton's law of cooling. So that means, okay, so here we use T as temperature and variable is time. So it's the rate of change of the temperature is negative K T minus T M. Okay, this is called cooling law. So that means you don't need to know this. This will be given. Okay, cooling law. What's the meaning? Rate of change in temperature is proportional to the difference between the temperature of the thing and room temperature. And this one, Tm, is called surrounding temperature. Oh, medium temperature. Okay, temperature. So for this problem, that is 70. Tm is 70 because the room temperature is 70. Now let's write down our information, all the information we have. So we want to find T temperature function in terms of time, okay? Variable TT, we want to find it. So our goal, we want to find this one. And let's see what's the given information. Original temperature is 350, right? 350. And it's as beginning. Beginning means T is 0. So when T is 0, at beginning is 350. And after 2 minutes, the temperature of the bar, so T2, temperature of the bar is 210. And there's another information, room temperature, surrounding temperature, which is 70. That's all we have, right? 3 numbers. Now let's plug those numbers into our differential equation. Let's see, what do we have? dt, left side, okay, negative k we don't know. We are going to use the information we have to solve for k later. T minus 70. Plug in the room temperature or surrounding temperature. This is the differential equation we have. Now let's solve this differential equation. Next, solve. And we noticed this is separable differential equation. And the capital T is just like a y before. And the small t is just like a x, right? So we just separate capital T and the lowercase t. So it's going to be 1 over t minus 7 dt 70. Okay. And the right side, negative k dt. Is that right? Separate. Okay. And now integral both sides. And the left side becomes natural log t minus 70. And the right side becomes what? Negative k t plus c. Right? Same thing, we want to simplify. T minus 70 equals e to the negative kt add c. Okay, and this we can further simplify e to the negative kt times e to the c. Actually plus minus because we took off the absolute value, right? t minus 70, and we can combine those c together. So constant, same as before, we can write down them just as one constant. So we can just write down them as c1, or just write down c, that's easy, negative kt. Okay, so t equals what? 70 plus c1 e to the negative kt. And this is the general solution, right? General solution. But we have two conditions we haven't used yet. Those are the initial temperature and after 2 minutes the temperature. So we are going to use those two conditions next step. First step, we solve t function. Next, we want to determine c1 and k, those two constants, by using the given condition. So let's see, t0 equals what? It's like an initial value problem. Before we plug in like a t at 0, right? And we solve some constant, c1, c2. So same thing here. t0 equals, plug into our t function, look at this t function, 70 plus c1 e to the 0, and which is given 350. From here, can we solve for c1? Actually, this is 1. c1 is 350 minus 70, right? So, which is 350 minus 70, which is 280. Okay, c1 is 280. And now let's plug in. So t function is 70 plus 280 e to the negative kt. Next, we are going to use the second condition, t2, to find the k. So t2 is given, so plug in t as 2k. So replace t by 2, now k. And which is given by 210. This is equation just has one variable k, right? Solve for k. Now let's see, 280 e to the negative 2k, which is 210 minus 70, which is 140, and then simplify e to the negative 2k, which is 140 divided by 280, which is 1/2. Do you know how to solve this in the next step? When we have exponential function, take natural log on both sides, right? So when we take natural log, let me write down in the next step. This becomes negative 2k, natural log 1/2, and the k equals what? Negative 1/2, natural log 1/2. And here, in the quiz or midterm, you don't need to simplify. You can leave answer like this. Okay, you can definitely leave the answer like this. I'm going to change this a little bit. I'm going to change this into negative 1/2. I know this one is natural log 2 to the negative 1 power is negative log 2. So times natural log 2, which is log 2 over 2. So I just simplified my k. But if you don't want to simplify, you leave this answer, that's also fine. Okay, also good. This, all that, both are good. Now let's write down our t function. T equals 70 plus 280 times e to the what? Negative kt, right? Negative kt. So negative, and I'm going to put like this k as k and the t. So that is the solution. Okay, t. Now let's take a look at those two questions. We are going to answer those two questions. The first question, find the temperature after 4 minutes. So just plug in t as 4, 70 plus 280 e to negative natural log over 2 times 4. Here we can use calculator, okay? What's the answer? The answer is 140. After 4 minutes, the temperature is 140. Second question. We are looking for, so that means after how long is going to reach 100 degree. So we set T equals 100 and solve for T. So we set temperature as 100 here, solve for T. That means how long it takes, right? How long means time, the time required. So that means we want to find the time. Time required for this bar to reach 100 degree. Solve this. It's pretty easy. It's just algebra here. I'm going to do this a little bit quick. Should be 30, right? And divide by 280. And it's divide cancel the tens, so 28, 3 over 28, and take a natural log on both sides. And solve for T. So T equals what? Natural log 3 over 28 divided by negative natural log 2 over 2. So we can use, if we use the calculator, it's going to be 6.4 minutes. It's going to reach this temperature. So from this example, you can see it looks a little bit long, but it's not difficult at all. It's a application of the separable differential equation. How to solve the differential equation is same as before. Separate the variables x and y. So here is lowercase t and capital T, but same thing. And then solve the differential equation, simplify, and apply to the condition we have, and find the constant and solve the real life problem. It's very useful. You can see by using this, we can know we can set the temperature to be anything and see how long it's going to take to reach certain temperature, or you can see after certain time what's the temperature going to be. It's going to be. So in the homework, you will find a similar problem. Okay, and here's the application. So this will be in the quiz. Okay, we can stop here.